this principle, this general principle looks like this. We have two integrals, one on the left-hand side and one on the right-hand side. On the right-hand side, we have an integral of some quantity, which is to be decided and which depends on circumstances, in which dimension we are, what we'd like to integrate, and so on. And on the left-hand side, we integrate some sort of derivative of that object, okay? Some sort of derivative, which I just schematically denote by d omega. Now, the next question is, what do we integrate over? And we are integrating on the left over some domain d, and on the right, we integrate over the boundary of this domain. This is the boundary of d, okay? So, this formula represents a kind of trade-off between an algebraic operation, namely taking the derivative going from right to left, and a geometric operation, which is taking the boundary of your region. So now we'd like to see how this general principle plays out in different contexts. Okay? And what we discussed last week was one particular, in some sense, the simplest possible context of this. In this context, we took D to be one-dimensional. One-dimensional. And so its boundary, B of D, is zero-dimensional. It consists of two points. So here's the picture. Here is D. It's a curve in this case. And being a curve, we usually denote it by C. C for curve. Okay? And the boundary has 2 points. Like this. And also there's an important aspect of this picture, which is that we have to choose orientation. We have to say which is the initial point and which is the end point. We travel from here to here or from there to this point. So let's choose orientation like this. So we travel from here to here. Let's call this point A and this point B. Okay? So the formula which we learned last time looks as follows. We have, on the left, we have the line integral of a vector field F. So F is a vector field. Actually, let me rephrase that. So let me start from the right-hand side. Because see, the point is that the algebraic object omega actually is found on the right-hand side, not on the left-hand side. So I should really start on the right-hand side. And on the right-hand side, I have the values. I have, first of all, a function f on the plane. And what I have on the right-hand side is just that I evaluate my function at the endpoints, at the point B, and I also evaluate it at the point A. All right? And I take the difference. So this one comes with coefficient plus 1, and this one is coefficient minus 1, and that is a testimony to the fact that this is the endpoint and this is the initial point, which is due to the choice of orientation that we made. So this is the right-hand side. And I can really think of this as kind of integration of the function f over the boundary. Right? Even though it's a zero-dimensional boundary, so integration doesn't really make sense. What I'm talking about is really evaluating the function at these two endpoints. But it does fit the general formula, right? Because I have a function, that's my omega, in this case, and I have the boundary, which is 2 points B and A, and integration over the boundary is simply represented by the difference of the values of f at B and A. Okay, what about the left-hand side? On the left-hand side, I'm supposed to take some sort of derivative of omega, so d omega, and I have to integrate it over my curve C. Right? So my domain now is this curve C, and what I'm going to integrate is I'm going to take a line integral of the gradient vector field of my function. So this is this derivative, this is the real incarnation of the derivative of my function in this particular context. In different contexts, this will mean different things. In this particular context, the derivative simply means taking the gradient vector field, and then I simply integrate that gradient vector field over the curve. Okay? So what I get is the fundamental theorem for line integrals, which we talked about last time. And my point now was to emphasize how it fits this general principle. So you can think of this as the first application of this general principle, which is explained on this board. All right. So what we're going to do now is we're going to make the next step. But you have a question. The omega. Why did I? Well, I'm just saying that if you don't like an upper arrow, I will make it a sideways arrow, like this. Is that better? Okay. Don't read too much into the arrow. It's just to say what that the omega is in this context. Okay. Omega in this case is a function f. That's right, which is what I wrote. That's omega in this case. All right. Any other questions? All right. By the way, for our worldwide viewing audience, and we have a pretty wide worldwide audience, as it turns out, the lectures, all the previous lectures starting from lecture 1 are now being uploaded on YouTube, and so everybody can now learn what happened previously on Math 53. You know, the struggle, the intrigue, the romance, the broken hearts. It's all there for our viewing audience. Seasons 1 and 2, the unforgettable seasons 1 and 2. Okay, let's go back to season 3 though. I have to say, I saw the lecture 1 today, and it sort of made me a little nostalgic about it. But I remember the good old days when I first came to this classroom and saw all of you. It was a priceless moment. Anyway, so what we'd like to do now is we want to make the next step. We'd like to generalize it when the domain is two-dimensional instead of being one-dimensional. So now we generalize domain D is two-dimensional. And so what I'd like to do is actually kind of make a chart and make a comparison between the one-dimensional and the two-dimensional cases. So this will be the one-dimensional case, and this will be the two-dimensional case. So in the one-dimensional case, first of all, what is D? Okay, D is a curve, which I denote it now by C because it's a curve. So let me draw another picture like this, and we have these two boundary points. Right? And so what should be the analog of this when we generalize it to a two-dimensional case? It should be a two-dimensional region, obviously, right? This is one-dimensional, and the analog of this in two dimensions would have to be just a two-dimensional region. So what is it going to look like? Well, it's going to be some region on the plane, like this. When I draw this curve, I really mean the interior of this curve. Right? This will be D. This will be D. And the curve will actually show up now as the boundary. So see, this is a very important point, that now the domain is two-dimensional, but the boundary is one-dimensional. So now the boundary is an object which kind of looks like the original domain in the previous example. Okay, so that's the domain. So this two-dimensional region. This is a region, two-dimensional region. And now I will just keep denoting it by D. Will not change the notation. Okay, what about the boundary? So the boundary here, as we discussed, just consists of 2 points. 2 points. So I'll just repeat. I'll just draw them again. There's 2 points, right? What about here? Here the boundary, as I said, is this yellow curve. So let me draw it one more time, approximately. So see, now I'm not shading the interior of this picture. I'm really focusing on the curve. The curve is one-dimensional, and the curve shows up as the boundary of this two-dimensional region. So this is a curve, B of D. Okay. Next, what is omega? And I would like to think in terms of these formulas. I would like to define all of this data and then see what kind of quality I get from this, right? So what is omega? Here, omega was f, was the function f. And the derivative of omega was just a gradient of f, a vector field, which is a gradient of f. And so what did I do? I integrated f over the boundary, so I evaluated my function at the points b and a. But on the left, I was taking the line integral over the curve itself, right? That is the line over the curve itself, over the gradient of the function f. So now the question is, what should I do? What should I take in this two-dimensional generalization now? Okay, so I have to take something as omega. I have to take something which I can pair with this curve, because omega is supposed to be integrated on the right-hand side, right? Omega is supposed to be integrated on the right-hand side of the formula, and on the right-hand side, I integrate over the boundary, not over the region itself, which is two-dimensional, but over the boundary, and that's this curve. So I have to think of the most general integral that I can do over a curve, and we've learned such integrals. These are line integrals, right? So I should be integrating a vector field. That's a natural thing to do, because in this analysis so far, we're integrating over curves, we're integrating vector fields. Functions we also integrate, but in this case, it seems more reasonable to integrate a vector field. So what I'm going to take is a vector field f, and this vector field is going to have 2 components, p and q, and that's going to be a vector field. And so I will integrate it on the right-hand side over this boundary. But I also have to say, what is the derivative of this? What do I mean by the derivative of this vector field? That should be some expression involving derivatives of p and q, which I would then integrate over the two-dimensional region itself, and that would give me the left-hand side, right? So I have to decide what this is. I have to find out what this is, and then I can build the formula. And it's not obvious from the beginning. It's not obvious what that derivative should be. Well, likewise, it was not so obvious that this should be the gradient. So let me just give you an answer, and then we'll see what is the meaning of this. Okay. So the answer for this derivative is given by the following formula, which at first may look kind of strange to you, but then I will give you kind of an explanation how this could be derived. And the expression is the following: it's actually going to be a function, whereas omega here is a vector field. The derivative here is actually going to be a function. So it's kind of opposite. The operation of differentiation in this context does something opposite to what it did in the one-dimensional case. In the one-dimensional case, the original object was a function, but its derivative turned out to be a gradient vector field. And now we start with vector field, but we end up with a function. That function is a combination of partial derivatives of p and q, namely dq dx minus dp dy. Okay. So in some sense, it is like a derivative. It's not a derivative in any obvious sense, because we haven't talked really about derivatives of vector fields, right? All we know that it should be some combination of derivatives of the 2 components of the vector field. And there it is. It is a combination of partial derivatives of the 2 components. Namely, I take the second component q, differentiate with respect to x. I take the first component p, differentiate with respect to y, and I take the difference. So it is, of course, in the discussion, it is assumed that all my functions and my vector fields are differentiable, and in fact have continuous partial derivatives. So this actually makes sense. Okay, so let's accept this. Let's accept this formula for now. I'll get back in a minute to the meaning of this formula and how to derive it. But let's accept it for now. And so let's now see our brand new example of this general formula in the case when the domain is two-dimensional. Let's see what it's going to look like. Well, again, on the right-hand side, we know already what it is on the right-hand side. On the right-hand side, we integrate over this curve. Let me draw another replica of this curve. That's the boundary of my two-dimensional domain, and I'm taking the line integral of this vector field, which I could write it as f dot dr if you want, but because I have already represented f as a vector field with 2 components p and q, I might as well just write it in terms of p and q. So I'll write it as p dx plus q dy, and this is certainly just this expression. It's the same. This is the same expression. So that's what I integrate on the right-hand side. What about the left-hand side? On the left-hand side, now, I should have integrate over my domain D. And actually, someone pointed out last time, at the last lecture, that in this formula, I didn't keep track of how many times I put the integration sign. It was an approximate formula. I just wanted to use a sign of integration, just one sign regardless of how many times I have to integrate. But now I'm writing a precise formula. This was just a dividing principle. Now I'm writing a precise formula. So I would like to keep track of the number of integrals, which is the dimension of the domain over which I'm integrating. So now my domain is two-dimensional, right? And therefore, it should really be a double integral. It should really be a double integral. And it should be a double integral of the derivative of omega. But the derivative of omega I have given by this formula. So what I get is dq dx minus dp dy dA. And that's the formula I get. So now, if you've never seen this before, it looks kind of surprising, because so it's a formula which equates a line integral of a vector field to a certain double integral of a function over the domain, here over the domain, here over the boundary domain of this domain. Perhaps let me emphasize this by drawing again the domain. This is the domain. Right, this is the domain, and this is the boundary. So that is actually the theorem, which is the analog of the fundamental theorem for line integrals in the two-dimensional case, and it is called Green's theorem. Green's theorem. Okay. So, question. That's right, very good. So there are still quite a few loose ends here, which I'm going to now unravel. Okay, so then the first question is a very legitimate one, which is, which orientation do I take on the right-hand side? This is a very good question, because if I just write this formula, it actually does not make sense, right? Because a line integral of a vector field is only well-defined when I prescribe the orientation of the curve over which I integrate, right? And if I change well, there are 2 possible orientations. In this particular case, I'm dealing with a closed curve, a curve which does not have a boundary, as you see. right? So the way I will be referring to the orientation is I'll be saying it's clockwise or counterclockwise. So there are two possible orientations. In other words, I can go like this and go around, or I can go like this. There are only two possible choices. So you can say, well, what's the big deal? It doesn't matter which choice I take. There are not so many choices. Well, it does matter because I get two different answers this way. Granted, the two answers only differ by sign, but of course sign is important because if I want to say that this is actually equal to this, I have to say under what assumptions and in particular under what choice of orientation. And so the point here is that the orientation has to be chosen counterclockwise. For this formula to be correct, I should take it counterclockwise. This is not to say that the integral with the opposite orientation is not well defined. It is also well defined. It's just not going to be equal to this. It will be equal to minus this. You see? So this is a very important point. The second point that I would like to make is this distinction between closed curves and open curves, or curves with boundary. You see, there is a difference. This is a curve, and there is also a curve in our previous example. These are both curves, and the word curve here refers to the fact that they are one-dimensional objects, but they are very different. This one has boundary, has non-empty boundary. It has a boundary which consists of 2 points. But this one does not have a boundary, or more properly, it has an empty boundary. Such curves are called closed curves, and it is interesting that it is exactly such a curve which shows up as a boundary of a two-dimensional region. So, a curve like this is called a closed curve. Closed curve. It has empty boundary. And you should contrast that to a curve with a non-empty boundary. This is not a closed curve. This is a curve. Well, terminology here is slightly misleading because a mathematician will also say that this is closed because it does include the boundary points. But when we say closed in this class, we will mean a curve like this. The closest on itself, so to speak, right? This one, strictly speaking, is also closed because I cannot say it's an open curve because I do include the boundary points. So let's just say it's a curve with boundary points. So curve with two boundary points. And of course, that immediately begs the question: is it possible to have such a curve, not a curve like this, but such a curve as a boundary of something two-dimensional? What do you think? Yes. Well, any other answers? Not that there are too many answers here, right? But if you think about it, you will see that it looks like I'm giving you an example of this curve being a boundary of the shaded region. But that's not true. What about this part? What about this part? Now, granted, both if I include this and this would be the boundary of something, but then it would have to go to infinity, or it would have to close somewhere, you see. So the regions which we will consider in this case, the regions like this, the regions to which we will apply Green's theorem, these regions are going to be bounded. They don't go to infinity. Yes? Yes? That's right. Let's go back to this. So the question is defined to be is counterclockwise defined as positive, right? So the terminology, we are free to make any terminology we like. We can call it positive, negative, whatever we want, right? Some people like counterclockwise, some people like clockwise. The standard terminology for this is counterclockwise orientation, counterclockwise, and the standard terminology is also called positive, but it's a matter of choice. Again, I'm free to take line integrals over any curve I want. I could take it over a curve oriented this way, oriented that way. My interest here is to choose an orientation for which this theorem is correct. And I know that if one of them is correct, it cannot be correct for the other one. So I have to make a choice. And the better way to think about it is as follows, which we'll need to slide generalization of this, for which this rule that I will explain now will make more sense, or will be more sort of easy to remember. Right now it looks kind of ad hoc. Why do I choose it counterclockwise? So the actual rule is the following: that if you imagine somebody walking on the, let's just a sketch. Somebody is walking on the boundary of this domain, right? So it's like, more realistically, I would have to draw this domain on this stage, and I would be walking on the boundary. So the rule is that the orientation of my path should be such that the domain is to my left always. It's to my left. Well, you have to choose it some way, right? So this is well defined. If you walk this way, it's to your left. If you walk this way, it's to your right. So it has to be to your left. Orientation to the left. To the left. Domain to the left. To the left. It does sound a little ad hoc, but actually it all makes sense in the end. So believe me, it is a good rule. And anyway, it's a rule for which everything works. Okay. If you choose a different one, you can do that, but then please put a sign. Change the sign on either side, on one side, not on both sides. Okay. So let me go back to the issue of boundaries. First of all, the domains that we will consider, domains like this, will have to be bounded. Bounded is something else. Bounded is something which doesn't go away to infinity, off to infinity. You see what I mean? So the entire plane is not bounded, and this is bounded. This is something we talked about when we talked about double integrals. When we do double integrals, we usually do them over bounded domains. If you have a bounded domain, its boundary would have to be a closed curve, you see. So this is important. This is a very important observation, which is maybe it's not so obvious at first, but it is correct. Now, there is one other subtle point which I guess I should mention, which is that it looks like this curve is slightly, this is not really, you can say it's not really a curve, it's a combination of 4 different curves. Right? Whereas this one looks kind of smooth, although I kind of messed it up a little bit, so it's not so smooth. I was trying to draw a smooth curve. This one is not smooth, it has 4 corners, at least. Right? But in fact, for all intents and purposes, these are both curves. In other words, I will think of this entire thing as one curve. This curve will have 4 different segments, which are smooth. And such curves, we will call them piecewise smooth. In other words, they're built from pieces which are smooth. The curve itself, the entire curve is not smooth, but it's a union of pieces which are smooth. In this case, 4. So when I talk about the boundary of this region, I can say that it's a combination of these 4 pieces. But I will usually just say it's this curve. I will ignore the fact that there are some coordinates in there, because after all,